Each one of these uranium fuel pellets releases enough thermal energy to produce 1 million kilowatt hours of electricity.
Enough to power thousands of homes for an entire year. See the energy here, visualized in the reactor's heart.
But have you ever stopped to wonder how enriched uranium is actually made? This is the bridge between raw power and the lights of the city.
How can something the size of a peanut hold that much power?
Today, we're visiting the world's largest high-grade uranium deposit.
Yes, deepest part of the mine.
To find out how one of the most dangerous materials on the planet is turned into clean energy. Stay with me until the end, because this journey into the heart of nuclear energy will change the way you look at the world.
Natural uranium consists of 99.3% uranium-238 and just 0.7% uranium-235.
The process of artificially increasing that proportion is what we call enrichment. We increase the concentration of U-235 for specific applications.
They developed enrichment techniques using gaseous diffusion and high-speed centrifuges. The most dramatic outcome was the Little Boy atomic bomb, which used highly enriched uranium-235.
After the war, attention shifted to the peaceful application of nuclear technology.
For use in power plants, uranium only needs to be enriched to between 3% and 5% uranium-235.
The critical difference lies in material potency. Civilian power is low-level enrichment.
Today, enriched uranium fuels reactors that generate roughly 10% of the world's electricity.
Countries like Australia, Kazakhstan, and Canada together account for more than 60% of global uranium production.
The element is primarily found in a mineral called uraninite, typically at concentrations between 0.1% and 2%.
But in the Canadian province of Saskatchewan sits the highest-grade uranium mine on Earth,
where ore concentrations can exceed 20%, up to 100 times richer than the global average.
The challenge is what lies above the ore, a thick layer of sandstone completely saturated with groundwater.
To extract the uranium without flooding the mine, engineers use artificial ground freezing. They create a solid wall of ice around the ore.
Pipes carry calcium chloride brine, chilled to -22 degrees Fahrenheit, to freeze the water in the sandstone.
This sub-zero liquid freezes the water in the sandstone, creating an impermeable frozen barrier that isolates the ore.
You see the scale of this cooling system? This required 200 pipes. Incredible. Each one taking up to 8 days just to install.
Extraction begins with a narrow pilot hole that guides larger drilling equipment to the ore body. Once the pilot hole is ready, massive remote-controlled machines move into place. A reamer drill then widens the shaft and breaks the ore apart. These tungsten carbide studs are designed to chew through solid rock. The drill head spins with immense torque, grinding into the dark ore, sending fragmented rock tumbling into collection chambers below. The entire process is operated by remote control, protecting workers from both cave-in risks and radioactive exposure.
The mine is continuously ventilated, with fresh air circulated every 20 minutes.
Welcome to the core of our operation. Every truck, every load is meticulously tracked through our advanced digital monitoring system. Typically between 15% and 18%, which is considered exceptionally high quality.
The ore is crushed, ground into a fine sand, and mixed with water to form a slurry.
This mixture is then pumped to the surface to begin its journey to the processing mill.
Specialized trucks haul the uranium slurry to a processing mill about 50 miles away. At the mill, the slurry is treated with acid, which selectively dissolves the uranium.
This leaves other minerals to settle at the bottom of the tanks, while the uranium is drawn off.
The uranium-bearing solution is drawn off and purified through a series of chemical reactions.
The primary target is secure and operational.
Engaging system override. Confirming authorization.
Authorization confirmed. Initiate transformation sequence.
The uranium is converted into gas and fed into high-speed centrifuges to separate the isotopes.
Being fractionally lighter, uranium-235 concentrates toward the center of the rotor.
These drums are clearly labeled with radioactive hazard warnings and shipped to a fuel manufacturing facility.
The enriched gas undergoes further chemical transformations here, moving through different oxide forms to create the stable fuel. Using several tons of hydraulic pressure, that powder is compacted into small cylindrical pellets.
Roughly the size of a peanut. These uranium pellets are incredibly dense. The staggering truth is that this one tiny pellet replaces nearly a ton of coal, showcasing the concentrated power of nuclear energy.
Or roughly 150 gallons of oil. Now hold that thought. Look at this tiny thing here. That is what we are comparing it to.
The pellets are loaded into industrial furnaces and sintered for 24 hours at extreme temperatures.
This process eliminates internal pores, increasing the material's density and structural stability.
The tube ends are sealed by automated welding to form finished fuel rods. 37 fuel rods are then bundled together into a structured fuel assembly. Each assembly is weighed with precision to verify the exact uranium content.
The relentless precision of machinery ensures that every component meets the highest standards of safety and quality. Once delivered to the nuclear power plant, the fuel assemblies are loaded into the reactor core to begin its life cycle. The core holds up to 5,760 rods across 480 fuel channels.
Fission begins when neutrons collide with uranium-235 atoms, splitting them and releasing energy. This self-sustaining chain reaction generates immense heat, which is carefully regulated.
The reactor itself is encased in 6-foot-thick reinforced concrete walls, the containment shield, military, and is designed to shut down automatically if temperature or pressure reach critical thresholds.
Housed in buildings 1,300 feet long and the equivalent of 20 stories tall.
Spinning at 100 revolutions per minute, each turbine drives a generator. We marvel at the sheer scale of the machinery required to convert steam into electricity.
The energy generated here is powerful enough to light up cities. It is capable of powering over. After roughly a year in operation,
the fuel assemblies are spent. Capable of powering over 756,000.
They must be submerged in cooling pools 26 feet deep for at least 10 years before they can be safely managed as waste. These repositories represent the final chapter in the life cycle of enriched uranium. These materials must remain safe from the outside world.
Thank you for watching this journey into the heart of nuclear energy. We've explored the process, from the mine to the city lights.
If you have suggestions for our next video, share them in the comments below. Don't forget to like, subscribe, and stay tuned for more stories through Stories Behind Everything.
Produced by John Doe.
Directed by Jane Smith.
Written by Bob Johnson.
The temperature is stable. Reactor core operating at optimal capacity.
Affirmative. Final oversight complete.